Okay, then next speaker up is Theo de Raadt from the OpenBSD project, and he's going to talk about the arc4random history. And as we all know, entropy is far too important to just leave to chance. I actually don't remember. I can figure it out, but it's a good quote, and it's old. It's from the old Rand paper where you were supposed to pick with your finger and get a decent random number. I hope the algorithms have improved since then.
Okay. Is this better? Okay. Okay, here we go. So that's an old, this is actually just from the Wikipedia page. I originally was going to use fuzzy dice because they're still popular in Canada. And I was actually going to pick up a set and give it out to somebody in the audience. But I found this on the Wikipedia page, like a couple of 100-year-old bone dice. So I'll start off with a brief history of how arc4random started in OpenBSD. I guess it all starts back in 1996 when somebody broke into my syslogd. OpenBSD was about a year old, maybe a year and a half old, and somebody broke into my syslogd. And the result was that a source tree audit started. It didn't take very long before we started noticing that randomization in our tree was a pretty significant problem. And the place where this all started, see, when OpenBSD started, I was the person who'd actually gone and written the YP client code. So I was quite familiar with the RPC code. And so I very soon went into the RPC code and revisited the scenario where the RPC identifiers were basically just starting off with a random, well, that's an awesome seed. That's the old seeding construct everybody used to use, of using get PID XORed with the time. And this is back in the old days when PIDs were not randomized, and tvsec and the time values were fairly well known on machines because there was no NTP. And this used to be really cool because it turned out back in the old SUNOS 4.0.3 days, YP-bind was always process 666, fantastic PID, but the time was also known because you could judge almost quite simply, you could judge how long it had taken for YP-bind to start since your machine had actually been booted. So people could actually figure out what the RPC IDs were for early YP. So I revisited this quite quickly and discovered that the algorithm was still all the same, and we wanted to fix this. But notice, even though this is code from 1996, I found this in the FreeBSD tree 3 days ago. So these problems still exist over there. I think it's great that they've actually gone and added the 32-bit casts for tvsec to ensure that, to deal with 2038. So the nicely will truncate that time value. Okay, anyways, it's to be forgiven. I mean, of course, this can be fixed. But it's everywhere in everybody else's tree, this problem is still unresolved. So just an example of something very, very minor, where this should obviously be a random number. A similar thing came very soon in the project, which was the DNS resolver. And the DNS protocol has a 16-bit ID. And in all of the old implementations, it would start at 1. And every single time a new packet is sent, it would simply be incremented. The solution we worked on was to come up with a non-repeating random number generator. So the idea is that you want to be random, but you also don't want to accidentally return the value 7, followed by 7, followed by 7. A perfectly valid random number sequence. Could happen. But if you were to do that, it would really break the DNS protocol. So as a sub-team in the project, and there's some names over there, like Niels Provos, CoreSDI, Angelus, David Wagner, Damien and Marcus of OpenSSH. These people have all been involved in actually working on generation after generation of a particular algorithm, trying to make it solid. This is not the strict random number generator, but once again, this particular algorithm we wrote, it needed random numbers to be able to serve its purpose. So it became quite clear to us during this work that it was really critical to make sure that random numbers would be available at all times, in all contexts. You need them, and you don't want any excessive work. But there aren't a lot of random numbers left because everybody's been bike shedding. Not just inside the BSD projects, but on sci.crypt and all of the emailing lists. Everybody keeps on finding rules as to how random numbers should be done. And this is kind of like the research mindset. We will use random numbers, and we'll deploy a random number subsystem when we finally come up with the perfect one. And until we come up with the perfect one, we're going to have to tell everybody, no, there is no random number subsystem deployed in your standard library that you can't, so therefore you can't use it. So not one line of code in a regular operating system actually has strong random numbers. So if you're on a Linux system and you want to have random numbers inside glibc, you're going to have to go and open a device. The result is really that nothing is really improved, and people just keep on waiting for a subsystem like this to arrive in the general sort of ecosystem, the POSIX ecosystem, the ANSI ecosystem, and it just doesn't happen. Because there's too much focus on only creating random numbers for key material. Obviously, that should be really, really good random numbers, or for IVs, or for those type of purposes. But they're ignoring the fact that there's so many usage cases where people are still doing ID++, or they are doing seeding directly from the time of day or from the PID. And people are also ignoring that there's these problematic contexts where you don't want a cipher that has complicated setup and such like that. So I would like to suggest, what if we had a world where getting random number data was as cheap as actually just zeroing memory? What if we could make it completely high availability service, always available in all contexts? Now, I'm not going to talk about cipher selection. I don't care what crypto algorithm you use. I don't care which one you use. Because if you use one and select one and it's shitty, you're just going to replace it because obviously it's bad. So this is an irrelevant question. I don't care whether you use RC4, whether you use cha-cha or something like that. Obviously, you're not going to use some dumb construction like XOR or something like that. You're going to use something that's like well known in the space. But it's not an interesting question compared to the mechanisms that are required to actually build a high availability random number subsystem. So back to this, how the research mindset goes. They keep on focusing on only a few potential uses, but I want to get to describing what the problems are of where you actually try to fetch random numbers and use them. The real problems people face on applications and in libraries is that they need to get random data in threads. They need to be able to do it if they're in chroot, but your typical application that's written doesn't know if it's in chroot. And if it's in chroot, then it doesn't have a /dev_random interface to talk to. You may be out of file descriptors. If you're out of file descriptors, then you can't open a random device to go and do something. So what's your application supposed to do? It's supposed to hard fail. This is not a high availability interface. It has rules and restrictions and constraints that make your software harder to manage. And sometimes you're deep inside a library. This is a place where you actually really want the random numbers to show up. You want them to show up inside libSSL. You want them to show up inside libcrypto. You want them inside libc. And even in our circumstance, we want it in our DNS resolver in libc. And you're not going to go and open /dev_random in such a scenario and run out of file descriptors and develop and run into all of these problems. So high availability is the primary concern for our API. So ease of use. Ease of use, so anybody can call it no matter what. I'm going to talk about the history of how this happened. We notice this goes back to 1996. It's a long, long time ago. Around that time, Ted So at MIT, his random device driver code that he wrote for Linux, he dual licensed it almost from the start. And so Mickey was able to import this into our kernel and slightly rebuild an entropy collection framework for interrupts in the BSD style to feed the entire device driver. But it didn't take very long before David Mezieris of MIT and Niels Provost and I became convinced that the /dev_random interface was a low availability interface. It had the blocking modes that are still common in Linux. It could run out of entropy, and you'd have to wait. we already were very concerned about using ch roots in lots of spaces, so we were concerned about it going and placing /dev random device nodes in various places. It just didn't make much sense. So before the end of the year, David Mezieres and Niels had actually gone and written the first version of arc4random in libc. And it started growing up. As you can see here, now is a timeline that is almost, well, it's more than 10 years. Soon, we discovered that the initial version of arc4random would actually seed itself from /devrandom, then run inside the process context. And that still was not chroot safe. So the entropy seeding was actually moved to a sysctl-based method from the kernel. And then Marcus Friedel came along, and he attempted to fix fork safety, a brand new concept which ended up with like Ars Technica going and saying that libsSL has got a broken random number generator. The first time we attempted to solve this was in 2003 inside our libc functions. David Mezieres found papers talking about how the early byte stream out of an initialized RC4 cipher was weak, and therefore we discarded the early parts of the stream. And then almost a month later, another version of that paper came out from another author, saying you actually had to drop almost 3 times as many bytes off the start of the RC4 stream. Kurt started working on our early thread code, even before Philip Günther did, and he tried to make the arc4random actually callable inside threads. First of all, so that the thread library could actually call arc4random itself in those contexts, but also so that applications could go and call it. So there was thread safety from some of the higher level APIs, like the resolver and such that might be called in a thread context. Damien of OpenSSH came around and started trying to deal with the fact that for arc4random buff, people wanted not just a 32-bit value, they wanted a larger block of memory. Of randomness, and also he got concerned about the uniform issues. For example, modulus bias is quite a few times people will take a random number and modulus percent it against the value, but you end up with modulus bias. So we actually implemented an API that does not have modulus bias. In 2013, Cha-Cha was becoming highly visible. And libevent, no, not libevent, what's it? Ottery had gone and changed to a very, very nice construction for doing random numbers on top of Cha-Cha. And it's faster, it's not just faster, but the Cha-Cha initialization and the particular construct didn't require data to be dropped at the early part of the stream, like with RC4. So that change was brought in. Then I worked with Joel Singh, this is last year, at ensuring that the boot blocks would actually supply entropy, and I'll show more slides about that soon to show how the mechanism works. Much, much more recent, around the time that the libsSL effort starts, Matthew and Bob and B. Cook and I tried to see if we could make arc4random more portable to other operating systems, and also to bring bring some of these safe fork constructions and such in to our mainline code. And now we've been trying to push those out to the various operating systems so they get these things as well. So in a nutshell, if you deal with this API, the idea of arc4random is there's no setup. You don't have to do any setup, you just call it. If you want a random value, call one of these functions and it will succeed. The API is available in both the kernel and in Userland. On the kernel side, you can call it in almost all contexts. So if you are in the VM layer and you want to make a random decision, you just call it, it's free. You can call it in modern OpenBSD all the way from the start of main. Even, for example, in some of the architectures, quite early in the setup, you'll be able to actually call it due to a particular way that we've constructed the setup of the cipher. Inside Userland, the function has no dependencies upon the file system, so you can run it inside chroot. It has locking for the stream, so you can run it inside pthreads. All libraries may call it safely. I think this is actually wrong. I don't think you can call it safely in signal handlers. So it always succeeds, and it returns your random result. The definitions make it clear that there actually isn't a way to return an error from this function, from these functions. The first one returns your 32-bit value, the other one fills a buffer, and the uniform version will give you a number within the bounded space. Of course, all of this was highly influenced by needs of other pieces of software that were being developed in OpenBSD at the same time. Privilege separation arrived in OpenBSD in 2001. In 2002, we enabled it. We actually ended up shipping a release, and I was a complete idiot for not allowing it to be enabled in the release, and it would have hidden the OpenSSH hole. I was not convinced that the code was ready. Good times, good times, good times. As a result of privilege separation, more and more of OpenSSH was running on the other side of a chroot jail. It needed randomness in that space. IV construction, the IVs need to be initialized. You obviously have to deal with key-grade material. So we needed randomness there, and you can't open/dev_random. Even later on, sandboxing has showed up. For various operating systems. We use systrace in a very, very limited way to avoid the time of check versus time of use issues. And we've completely limited it down to a very, very small number of system calls. And you'll notice one of them in there is getEntropy, which is a system call that we use to actually initialize arc4random. It's a tiny, tiny amount of exposure to the kernel's system call interface. Really, really trying to lock things down. We're also influenced by the stack protector, which arrives around the same time. We needed to initialize the cookie with a random value quite early on. And it's not like you can start a process up and to get its cookie go open/dev_random. That is ridiculous. So instead, we used something quite low inside arc4random to go and initialize the stack protector cookie. Nowadays, things have gotten even more fancy. We use an ELF segment and actually pre-initialize it with random data in Userland and the kernel and precede these types of things completely automatically so that the very, very first instruction of the kernel or of a Userland application already have their stack protector cookie loaded into their address space. Okay, just a few more slides about the change to Cha-Cha. We replaced RC4 with Cha-Cha because Cha-Cha arrived. It's a better stream cipher. It's very important that we don't have to dispose of the early part of the stream. There's performance benefits out of it, and we'll change it again if we have to. And the best way to look at all of this is sometimes people go and say, hey, but it's RC4. RC4 is not a good name to have in an API anymore. So we wrote this in the manual page, trying to be a bit clever. It's a replacement call for random. And like it says over here, we use Cha-Cha for the cipher right now, the stream cipher. But if a better one came along, we'd switch in a heartbeat. And we don't care. It's completely invisible. It would not be exposed to anybody. There have been pushes to actually rename the function to something like good random. And there's a crowd of people who are actually trying to suggest that an API of almost exactly this behavior, error-free, should be pushed up into a POSIX, probably with a name like POSIX_random. I don't know. I'm going to talk about the kernel random subsystem and start showing some diagrams as to how the mechanisms work. The kernel gets its entropy from interrupt sources and random devices like built into the CPU, like the randomization instructions that are built into various processors nowadays in the normal fashion, much like a random number generator does on other operating systems. Nothing unusual over there. A major innovation is that the boot blocks actually participate in the setup of the initial seed early on. And there's a loop, there's a construction inside our RC scripts to ensure that the next boots actually collect more entropy. I'm going to just show it with some diagrams because it's easier than the words. At initialization, a file in the file system, /etc random.seed, is read by the boot blocks. And it is mixed with RDRAND instruction data, if it exists on that CPU, Or, for example, a counter that's on the CPU, or something else. This is architecture dependent. We attempt to generate a mix of data. And then that mix of data is used and fills an ELF segment inside the kernel that we've loaded into the memory. So that kernel, the minute its first instruction runs, already has a chunk of data in it, a block of memory that's random data supplied by an outside party, the boot blocks. Inside this ELF segment, we have gone and tied a variety of objects that we actually wish to be random right from the start. So the stack protector cookie is in there. This means that the first function in C inside the kernel that you enter will automatically go and take that stack protector cookie and save it in its frame. And of course, upon return, we'll verify that that stack protector cookie is the same to ensure that the frame has not been damaged in the standard stack protector way. We also completely overlay the cha-cha-20 random number state that's in the actual arc4random algorithm. So this means that arc4random, the kernel subsystem, doesn't even need any initialization code. Right off the bat, it already has a random state inside its stream supplied by the boot blocks. So the larger view, stepping back to a running system, is that after the boot blocks have gone and provided data into the kernel's entropy collection mechanism, the kernel then runs arc4random as a stream cipher subsystem, and each spawned userland process ends up with an arc4random generator inside its own address space, initialized in the same fashion, running independently in each process. And let's just bring it back to how does that seed file actually help ensure that we're good the next time? Because when we finally are shutting down the system and running rc.shutdown, that will go and do a DD and take data out of the random subsystem, in this case /dev-random, because it's a file system exposed thing, it's easier to do to use with scripts. And it will take that and go and replace the random seed on the root file system before we reboot, so the next time you're done. But what if you don't reboot? What if you crash? So we actually do exactly the same thing also early on in boot in the RC scripts to ensure that if you boot and you've just used that entropy off of the seed file, we immediately replace it early on in boot to make sure that the next one at least is unique in some way. But it's not a great file because you've taken entropy, rolled it in, and only had a couple of interrupts by the time you do this. So it is actually better to also do one at reboot. That'll be a better seed file than this early seed file. And I'll show more sort of the framework of how the standard entropy subsystem flows its data forward and actually turns into a cha-cha stream, which is usable by the kernel. So we have the standard RD-RAND and interrupt latencies and such as that feeding into an entropy queue outside of the lock. And we whiten that using some sort of crypto algorithm. Who cares? Just sort of bit spreading one. Once again, it's irrelevant which one we use. If it's not a good one, we'll use another one later, because this is more about the mechanism. And that goes and initializes a cha-cha state, which has been pre-initialized because it's in that ELF random data segment. And off of that, we have a cha-cha stream, which the kernel itself goes and uses for a whole bunch of functions, like the address space randomization inside the kernel, the PID generation. Every single IP packet has an IPID in it, which is initialized with a random value. And for output to /dev-random, or the get entropy system call, or ELF random data segments, which we place inside userland programs. So many, many consumers fall off the bottom of this single cha-cha stream in the kernel, and they slice and dice and take a component of this data flow. I just want to show sort of the initialization that sort of happens early on. So early on, this cha-cha state already contains some data. It's already been splattered by the boot blocks to ensure it's got some random data. But still, we do think that we should do some sort of an initialization. So we take, whenever this happens, we take a piece of the entropy coming from the interrupts and stuff like that, coming out of the queue, and we fold and mix that in to create a new cha-cha seed. And at that point, we run a new stream. And it's the same with reinitialization at some later point. It's a mix of the whitened data coming out of this entropy queue. We mix that, in the same way with an old cha-cha state. And we follow a principle which Matthew and I have been calling something old, something new. So you never only rely on new entropy. You always use a part of the old state, because the old state has had data taken away from it. It's been eaten away at the cha-cha state, and it's got some content. And that content it's got is actually fairly good. It's folded and mashed and stuff like that. So we mix that in with the entropy. We never rely just on entropic whitened data coming back down. And of course, we have the old school sort of semantic that if you write to /dev_random, you can supply entropy yourself as well. So we have that as well as an additional mixing method. And this is fairly popular in the other operating systems as well. And there's the reboot example, of course, showing that out of this engine, we're writing this random seed for the next boot. I want to talk about something else we're trying to do with our stream of random data. We often try to share it between multiple consumers in the same context. So if you just imagine a stream cipher there, the idea is that different consumers inside the same context, like the kernel is a single cha-cha context, but each userland process is a separate cha-cha instance as well, so it has its own stream. Different consumers inside that space can go and take parts of the stream separately, cutting out components they want. I just want to sort of bring this into like the idea of a userland program. It's just a bit of an example, not really specific. It actually is a piece of code that I saw, and I've sort of tried to visually explain what this piece of code would do. So imagine you have an application that's dealing with a block of memory, but meanwhile needs to do a DNS lookup. And somewhere inside the DNS lookup code ends up calling malloc. And malloc goes and gets random data to do some address-based randomization. The resolver goes and packs an ID in, so it needs some random data. And then, since the resolver is now done with a piece of memory, now it needs to free it. And our free code actually also uses random data to ensure that the recycled objects inside free are sort of missorted to ensure that future small allocations will not be as predictable. And then the application goes and does a new allocation. So you basically have a few different parts, even of different libraries, sharing on the same random stream, taking tiny little pieces of it for themselves. And I think this is very important for two particular concepts that you see once in a while in crypto research papers, which is backtracking resistance and prediction resistance. So we're all being told that these stream ciphers like cha-cha and such are excellent. And we should probably, like Bernstein says we only need 256 bits, initialize the cha-cha, and go for the life of the system. And it's going to be a good enough stream cipher. But what if it isn't? This is a very free operation that basically allows us to just take chunks out of it. Because we have so many additional consumers going and taking data out of this stream, now you're going to say synchronously, but I'll explain why it's not synchronously. Therefore, it's very difficult to predict what was there before, because something else small may have gone and taken a chunk out of the stream. And so your view of the stream, if you were a large collector, would not necessarily be able to give you enough to replay and figure out why the stream cipher was in a particular configuration. You wouldn't be able to discover the inner state. And same with trying to predict what's happening in the future. You can't even predict that as you're doing a large collection of data future down the stream, whether something else will interpose and actually take a piece of data out of the stream for you. And you're going to say, but this is under program control. And under program control, it's deterministic. But many pieces of software we run are actually not deterministic at all. Like a threaded web server is not deterministic. It has requests that come into it asynchronously at various times. It has short reads, short writes. It does allocations. It does all sorts of other random things. And in OpenBSD, this works because our malloc gets involved in almost all of these transactions. In other systems, if they don't use random data in their malloc or deep down inside their libc, they probably don't get this particular construction. There's no formal proof, but I feel good about it. Does anybody else feel good about it? And there's lots of these things actually going and slicing up and going and grabbing random data asynchronously. In the kernel especially, asynchronous events are everywhere. So we've got our random PIDs being forked, thread IDs, other sorts of decisions. The address space randomization out of mmap is using a ton of random number data as it goes and decides, not just the addresses where to put your physical pages, but also it's making decisions as to how to restructure the VM trees, the virtual management mapping trees, to make them not actually be very expensive for the caches and the TLBs and everything else like that. We've got packet creation. So you flow a packet through and an IP ID is put on the packet. So that's just a very small number, but it's perturbing the stream. And pfNat is making also decisions to pick port numbers and such like that. We have standard port allocation for applications to grab the port number, like for a socket, for like a bind. And the scheduler is making decisions which do have some randomness incorporated into them. And simultaneously, you have userland processes. And they come along and they decide that their RC4 generator has expired and no longer has a valid state. And they need to get new entropy for it, so do a get entropy call. And they take entropy out of the kernel RC4 cha-cha stream. And then in userland, the primary one, like I was mentioning earlier, is the malloc subsystem. We called auto malloc because the developer works on it as auto. So all of these little random decisions are used on a regular basis out of the stream to go and do this. And it does this perturbance. And if there's any DNS happening inside your application, that'll happen as well. And the shared library linker is also making randomization decisions for how it lays things out. The primary thing I think that the shared library linker does with randomization is if you load a bunch of libraries, it will randomize the libraries before mapping them. I'll talk about this reseeding in userland. This something new, something old, something new principle is here. libc arc4random recedes when too much volume of data has been pulled out of the stream. We don't trust it anymore, and it's just better to just go and reseed it. This is actually, because we use cha-cha now and we don't use RC4, we could probably actually extend this and do it much, much later. But for the moment, we've left these values, the amount of time and the amount of volume unchanged, because it doesn't have a serious performance impact. A very important thing, though, recently fixed, well, I think in my original slide I said we tried to fix it in 2002 or something like that, is the fork detection logic. When libsSL came out, somebody pointed out that, the fork checking was incorrect, and the grandchild process could actually get a view on the same stream as the grandparent. So the fork logic underwent a fairly major set of changes. In our portable code, we started using pthread at fork on systems where it's safe to go and clear the state and cause the child of the fork to reinitialize itself. And on OpenBSD, a different mechanism showed up, where we actually now have a madvise. Is it madvise? It's madvise. Thought I heard madvise. We have an madvise flag that you can set on a page, so that at fork that page will be zeroed, and then the libc code notices that post fork, it's the thread, the cha-cha seed state is completely cleared and goes and reinitializes it. And I want to make a warning over here, because many systems actually have this broken still because they have not caught up with our code. I believe that NetBSD has this fixed. Apple has this fixed. Google has this fixed in their version of this code. And FreeBSD does not have it fixed. And you guys have had a lot of warnings. You should get this solved. You should resolve this immediately. So that's what the recent important work was. It was to fix this reseeding, to ensure that the boot blocks bring seed material in, and completely simplify and remove procedural initialization through the code flow. We added this new get entropy system call to seriously simplify the direct interface of getting entropy and separate it from this heavyweight sysctl system call, which has way too much potential risk in it, and we do not want it inside chroot spaces. So I actually would think it would be great if some of the other projects actually work on adding a get entropy. It's a tiny, tiny little stub. Tiny little stub. It's the same as CCTL code. Just copy it and make it a system call and move on. And we have these random data segments that we actually now use inside our kernel and inside all of our applications to provide data without actually asking at a system call layer. And we've been working on portability to other systems. So it's available in lots and lots of places. And anybody can use it for anything. This is a neat hack that showed up in Slovenia. I was talking with Ted, and he actually implemented it. The hack is that even sRandom_dev, which I think is a FreeBSD addition to the random/sRandom API, probably dates back to 97 maybe? Well, the new change that's happened is if sRandom_dev is called, then obviously the sRandom_dev was basically just a way to go and ask /dev_random to provide a seed for the existing stupid standardized random LCG, whatever. But in this case, if sRandom_dev is called, then random actually becomes a direct call to arc4random. So you actually end up with a non-seeded proper algorithm. So it's funny because old legacy code, which doesn't want to be updated out of the sRandom and such world, can actually, if it calls sRandom, suddenly it has real arc4random. This is where the API is in use. Android has had this from the beginning in their libraries, but they changed the name. They have a different name. It's on BlackBerries because they copied it out of NetBSD's version and QNX, and I think they updated theirs. Mac OS got a FreeBSD version and has kept it quite updated. So it's pretty much everywhere except for in glibc. And now I'm going to go say, but it's not in Solaris. But it doesn't really matter because many applications and libraries have their own arc4random versions directly in them. For example, NSD and Unbound and a whole slew of other applications just directly have it themselves. And we're trying to find a way to help the Linux people get to an interface like this as well. So Bob Beck and I worked to encourage Ted to actually go and add a get entropy interface to Linux. And it turned into this thing called get random, which has got like 6 ways that you can misuse it. And I'm a bit scared because it looks like instead of creating an arc4random type layer fed by this entropy subsystem down below, it looks like the applications are now going to start using get random directly. And it's a very, very easy API to misuse. It acts like get entropy as long as the amount of data you request is 256 bytes or less. But as soon as you ask for more than 256 bytes, it has the potential to sleep and the potential to return EENTER and a whole slew of other misbehaviors. So I'm worried, and a bunch of us are going to have to keep an eye on the application space to try to encourage them not to go down the wrong road. I think I can actually suggest how popular it is. So it's just Googling for it. It's pretty interesting. But it's really funny where it shows up because I think all of those are actually for using arc4random in iPhone apps. Because Apple went and exposed arc4random in all of their APIs for all of their app developers. So if you actually Google for something interesting about arc4random, I think you have to go pages and pages and pages and pages down before you actually find something Unix related. Okay, and that's it. Are there any questions?
No questions?
Really?
This must have been all too clear. Then we thank you for a very precise presentation. Thank you.